So back in our imagination room, we're going to continue talking about hypothesis testing. And so we left off with looking at the regions of the normal distribution and the 3 steps of hypothesis testing, ending at right before we actually did step 4. Because step 4 makes a little bit more sense when you have some context. So let's actually put this into context. If we think about it, let's look at an example. An example could be college bookstores, right, and textbooks. So if we give an example, the college bookstore tells prospective students that the average cost of its textbooks costs $52, and the standard deviation is $4.50. A group of smart stat students thinks that the average cost of textbooks is actually higher. In order to test the bookstore's claim against their alternative, the students are to select a random sample of 100 college books. Assuming the mean of the random sample is $52.80, perform a hypothesis test at the alpha level of 0.05. All right, so let's break this down. If we look at it, we have to first think about all the pieces of the puzzle. I always tell my students the pre-step before you run any type of problem solving or word problem is to pull all the pieces of it, especially because it'll make more sense within the actual 4 steps. So if we look at the first piece we pulled out, we're going to think about pulling out the mu, which is the mean of the population. The college bookstores, they were saying that the cost of the average textbook was $52. The smart stat students are saying, no, we actually think it's higher. And when they actually ran it, right, they actually got a mean, which means their sample had a mean of what? $52.80. So what you're really trying to test, right, in hypothesis testing, is this 0.80 cents? If this 0.80 cents is significant enough, is it significantly different enough, these books that they selected, from the actual average cost? If this 80 cents, once you collect more random samples and more random samples, actually leads to $53, $55, $65, then you're actually starting to realize there is a significant difference between the cost of the actual textbooks and what the college bookstore is claiming. But if you were to add on more samples, and this number would become smaller, in other words, closer to 52, this sample is actually a representative sample. And like we were talking about before, that means that this sample actually falls inside the HO's house, the 95%, if we're testing at a 95% level of accuracy. And if it didn't, it was in the tail. In other words, extremely different than what the college bookstore was saying. This sample is different. So what was their sample? They had a sample of 100 college textbooks. And the average cost of the textbook for the population was $52, and they said the standard deviation was $4.50. So in other words, they're saying, what is the standard deviation again? How high and how low you can go from the 52. In other words, the cost of college textbooks can be as high as $56.50, or it can be as low as $59.50 or $58.50. My math isn't that good right now, right? It can be as low or as high. So in other words, you're adding and subtracting to this number, and that would be your range, about 58 to 56, in terms of the cost of college textbooks. This is within that range. So if we add on more samples and more samples of 100, would this be outside of the range or would it be inside the range? Because hypothesis testing is a statistical mathematical procedure for telling you if that sample is extremely different than the population. In other words, as compared to the actual standard deviation, or in this case, the standard error. So let's actually run it. If we're running it at an alpha level of 0.05, we have to then do all the steps of hypothesis testing. Let's start with the first step. The first step says state your hypotheses. So we're going to have a hypothesis null and a hypothesis alternative. The hypothesis null says there is distinctly no difference between the population and the sample. In other words, what you're doing and what's already been done. And remember, if we're talking about a one sample z-test, this is a standardized test. So in standardized testing, all of the means convert over to 0, right? Because the standardized z-test is a bridge, right? It's comparing. It's allowing you to identify every score on its distribution, and then it's going to allow you then to standardize a distribution and make different distributions comparable. In other words, comparing apples to oranges. 2 things that would be measured on different scales cannot be comparable once they become standardized. And in a standardized distribution, the mean becomes 0. So in hypothesis testing, it would say the mean of the population equals 0, right? Theoretically 0, which basically means $52. and the mean of the population would be not equal, or greater than, less than, greater, less than, or equal to. Where did these symbols all of a sudden come from? Remember we were talking about there being a one-directional or two-directional, in other words, a one-tailed or two-tailed test. When we were actually conducting research, if you're basically stating there is no difference or there is a difference between the sample and the population, what you're doing and what's already been done, you're talking about a two-tailed test because you're not specifically saying where the difference is. You're not saying if the difference is on the higher end, the lower end, increase, decrease, lower, higher, bigger, smaller. You're not stating any of that. You're just simply saying it's different, giving you two places where the difference could lie. But if you said, like in our example, the group of smart stat students thinks the average cost of textbooks is higher, they actually stated where they think it is. They believe that the cost of textbooks is on the higher end. So they're not testing for the lower end. They're only testing for one particular place. So the symbol not equal means it can be in either side. These symbols, greater than, less than, or equal to, means it's in one particular place. And in this instance, they're saying that the average cost is bigger than 52. So greater than the 0 or greater than the average, which is $52 in this case. So there are your two hypotheses, the null and the alternative. When you get to step 2 then says set your criteria, your alpha level. The test told you what it was. And also keep in mind that the default is always going to be 0.05. In other words, 95% accuracy level of testing. The majority of the time, even when you run through SPSS, like the stats programs, they always default at 0.05. You actually have to make your test more strict. So think about if you're talking about DNA testing or you're talking about other type of testing, they're 99% accurate, 99.9% accurate. Those are actually the probability and the alpha levels of accuracy. How strict do you have to be in your testing? So you only have a margin of error in 99% accuracy of 1% of being wrong or being extremely different. So that's what we're talking about here. If we're saying 5%, we have a 95% level of accuracy with 5% margin of error, or 5% in a place where you can be distinctly different. And being different might not always be a bad thing. Keep that in mind. So our alpha level in this test, it told us it was 0.05. So then in reality, you already know what it is. In other words, we're testing at 95% level of accuracy. And just to take a quick pause, when we're talking about this level of accuracy, who chooses the alpha level? The alpha level, like I tell my students, is chosen essentially by 3 different entities. The first one could be you, the researcher. If you've got the power, by all means, choose it. 95% is the min that you could be. You could be 97, 98, 99, but never less than 95. The second one would be if you're talking about the researcher and in terms of the funder. So who's paying for the researcher's work? They might want tests being ran at 97, 98, 99 level of accuracy. So they might say, you know what, I think my test needs to be a little stricter. So they'll actually tell you to make it harder. And if you're not talking about the funder who's paying for it, you, because you ain't got the power either, then what are you talking about? You're talking about the field of research. Because in DNA testing, everyone tests at 99.9%. Why would you test at 97? If you're talking about cancer research, you're talking about HIV research, you have to see what level are they testing at so you can even compete in that field. So in reality, it's chosen by 3 different entities. Yourself if you have the power, the funder who's paying for it, or the field of research. Keep that in mind. In this instance, like I said, it's 0.05. If we're talking about the second piece of this, it's talking about the critical region. The critical region is that number that's going to tell you where the tail begins. In other words, how big or small does your z-statistic once you run your test have to be? Is it going to be this number that puts you in a tail or this number that puts you in a body? You need to know where that cutoff point is. And that's actually called your critical region. And in this instance, what are we talking about? The z-critical value. The z-critical value comes, like I said, from the unit normal table. Every test has its own table. And so the unit normal table will tell you what percentage is in the body and what percentage is in the actual tail. And if we're looking at this, we're running a one-tailed test because we're only testing in one particular place. So in other words, a one-tailed test is here. We are only testing in this area, right? The positive tail test. What number tells us where the tail begins and the body ends. In other words, the entire 95% needs to be behind it in its body, and the entire 5% will be above it in its tail. What number gives us this? And if you look at the unit normal table, you're actually going to start to realize that that z critical is actually 1.65. When you look at the table, you'll see it's 1.65, 1.64, 1.63. There's nothing that's going to give you exactly the 5% in the tail. It's going to give you 505 or 495. Which one do you choose? You always choose the one that makes it harder to be in the tail. You want to be further in the tail, never less. You're never going to tell someone you're 94.99% accurate. You'll be 95% accurate, 97% accurate, but never less than 95. So whichever number gets you furthest in the tail is the one you choose. In this case, the z-statistic of 1.65. So in other words, if you start thinking about how all these are building up, you actually have your educated guess, then you have your criteria. And step 3 is going to be compute it or run your test. So if you look at how they build up, once you run your test in step 3, you're going to get a z-statistic. What do you do with that number? That's where these come back. Because that number, you have to know, is that number bigger than 1.65, which will put you in a tail, or is that number smaller than 1.65, which will put you in a body, and then you can decide which of these hypotheses were actually the one that you actually demonstrated. The hypothesis null or the alternative, which allows you to go on to step 4, which is actually making a decision. Are you significantly different or not than the actual general population? So let's see what that looks like. So z equals the mean minus the mu, the sample minus, right, the sample mean difference, the sample minus the actual population over standard error of m, which is standard deviation over square root of n, right? That's your standard error of m formula. And so let's plug in our numbers. What is the mean of our sample? 5280, right? What is the mean of our population? 52. What is the standard deviation? 450. What is the sample size? Square root of 100. Hopefully we know square root of 100 quickly turns into 10. And what is 450 divided by 10? Let's remove the decimal point over. So in other words, 45? Yeah. Then 5280, oh, it's not 45, 0.45. 1 second. Let me pull up the answer key just to double check that we are doing this correctly. Right? Yeah, 0.45. Just making sure I always make mistakes between my tens, right? So 0.45. 5280 minus 52 is going to give us what? 0.80 divided by 0.45. And essentially, what is 0.80 divided by 1.45? By 0.45, it all leads you down to 178. Now I ask you the question. Is 1.78 bigger than 1.65? Yes or no? It is, right? So where are you? In the tail or in the body? Because this red right here is 1.65. You are in the tail. And like I had told you before, this is HO's house, the no change, no difference, general population of 95%. And this is H1's house, the alternative hypothesis. So which one did you demonstrate? That you're just like everybody else, or that you were extremely different? You showed that you were extremely different because you landed in the actual tail. So the smart college students were saying that we believe the cost of college textbooks are significantly higher. And when they actually got a random sample of 100 textbooks and got this average cost of $52.80, they said, okay, look, we actually got a higher cost, but let's find out if that higher cost is significantly different and significant enough to demonstrate that the cost is actually going to be higher in the long term. In other words, when we collect enough sample of college books, we'll realize that this number is going to get bigger and bigger, not closer to 52. When they ran their test, they realized, yep, because I am in the alternatives house, I showed that there is a significant difference between this college textbook sample and the general population. So what did we say? We basically rejected the null hypothesis. You always go against the population. So did I reject or fail to reject? I rejected this idea. I didn't fail to reject it. I rejected it because I landed in the actual tail. So what's our decision? That there is a significant difference between this sample of college textbooks and the general population. And there's a whole way to write that up in APA statistical format. Essentially, what makes it APA stat format is writing this in a paragraph format and substituting all the different words for symbols. Anywhere you can say mean of, sample of, you actually write the letters instead of actually writing the words.